All right, good afternoon, everybody. So welcome. Hey, thanks. So welcome to CSE215, which is our discrete structures course. So let me go ahead and share my screen. All right, so hopefully everybody's doing well. It's been an interesting summer for sure, I know for most people. And we got some nice relief over the weekend from the smoke, but unfortunately I think the smoke is coming back. As it's coming in my apartment. But we will get through this. And we'll get through it with some discrete math and discrete structures. Alright, so welcome to the class. Bunch of stuff to go through. So this is basically an hour-and-a-half class, 3 days a week. So we'll get through the introductory material today, the syllabus and things like that, and then I want to actually start getting into some of the subject matter as well. So so lots of good stuff to do. So let me start off with Canvas. So if you're here, you've already got Canvas access because that's how you got the Zoom link, presumably. So I'm just going to run through some of the highlights on here, in particular the syllabus and such. But you know, Zoom meeting info, you can come here if you lose the info. If we have to change the meeting code and stuff, come back to Canvas and get the latest info from Canvas. That's where I'll keep the up-to-date meeting link. Office hours, so you can always go to engrcs.com, which you're probably familiar with. engrcs.com/schedule. And that lists office hours for myself, Izad, Tina, and Carol, so the whole engineering department. And you can click on my name and find dates and times for my office hours. If you click on more details, you'll get a clickable link for the Zoom meeting. And this is a different link from what we do for the classroom, okay? Every class has its own link. Office hours is a totally separate link. And this link has a waiting room set up, so if you try to talk to me in there and I'm already talking with somebody, you'll get a message saying waiting for the meeting host to let you in, okay? Doesn't mean probably that I'm not there. It probably means I'm sitting with somebody else right then. And usually when I finish with somebody and I let somebody else in, I try to send a note to the whole waiting room saying, you know, there's 5 people in the waiting room, I'll get with you as soon as possible. But it might be a while, so plan on having something else to do and have your sounds on so you know when I let you into the room. So that's the Zoom setup. Let's take a quick look at the syllabus, and then we'll dig into some of the other details. So CSE215, discrete structures. This is part of the 200 level CS sequence here at Clark. So 224, 22, 23 are the 3 programming classes taken in fall, winter, and spring. And then CSE215, discrete structures, people take that in either fall or winter. And this course really presents and explores some of the kind of theoretical underpinnings of computer science, the things that make computer science work for us. So we get into a lot of topics: logic, propositional calculus, set theory, trees and graphs, and languages and automata theory, and a whole bunch of different things. It's 7 or 8 different topics. It's an 11-week course in fall. So we get through roughly 1 topic a week. There's sometimes we'll spread out into a week and a half. But it's a fast-moving course. All right, so my name's Nick Macias. I'm your teacher. Hello. Best way to reach me: email me, nmacias@clark.edu. That works a lot better than emailing me through Canvas. Okay. So straight email to nmacias@clark.edu. That's your best bet. Textbook is an online text. It's open access, so it's free to download. This is a good text, and you definitely want to download it. I will give homework questions from this text, so just follow that link and pull it down from there. That's your best bet. should have made sure that works before I said all that. Yep, looks like that works. This is a good text. The person who wrote this did a really good job. There's a lot of topics in here that we do not go through, and there are some topics we go through that are not in here, and I'll give you other references for those. So don't, read the entire text and try to memorize it, because a lot of this stuff we don't get into. But we cover a lot of this, at least the topics themselves, even if it's a different presentation. Course outcomes, I'll let you read those on your own, but these are basically the things that you come out of the course knowing that make this a usable prerequisite for other courses like CSE215 and a lot of the third year computer science courses at WSU Vancouver. Approximate tentative schedule, we're going to start off week 1, that's this week, talking about some set theory. We'll start off with some stuff that's fairly obvious and rudimentary. By the end of this unit, we'll get into some fairly bizarre and disturbing aspects of set theory. Week 2, we'll start talking about logic. Week 3, some number theory. Week 4, we'll come back to logic and turn it into proofs, mathematical induction, and propositional calculus. Week 4 and part of 5. Week 5 and 6, we'll talk about counting. 1, 2, 3. There you go, we're done. Week 7, Boolean algebra, and then we'll go on to graphs and trees, algorithms, languages, automata theory, and we usually run out of time before we get through all of this, so we start cutting some of it out. I don't think I've ever taught this course and gotten to the end and said, well, there's nothing else to talk about, right? There's so much to this subject, and it's a really fun subject. It's a subject I enjoy, and a lot of students have told me that this, it ends up being one of their favorite courses. So we'll see where it goes. Homework, I'll give you homework assignments, roughly 1 per week, and they'll be worth a total of 15% of your grade. I promise to grade at least 1 question from the homework. I may not grade them all. I may grade 2 or 3. I may grade them all. It depends, but basically I want to try to get an idea of your understanding of the material. But I won't tell you which question I'm going to grade if it's only 1, so you want to do all the questions, right, assuming that they're all going to be graded. So 15% comes from homework. 15% comes from quizzes. There'll be, I think, 2 quizzes during the term outside of your main exams. There'll be 2 programming assignments for a total of 10% of your grade. Midterm will be 25%. Final exam will be 35%. Attendance, I'm not going to count for now. If attendance drops off or people don't seem to be participating in class, I'll go ahead and add an attendance component and take a few points away from one of these. Support services, if you're in CSE 224, you already heard me talk about this, but I'll say it again in here. Clark has a really large component dedicated to trying to ensure that every student has an equitable opportunity to learn whatever it is they're trying to learn, to accomplish what they're trying to accomplish. So if you are in a situation where, for example, having extended testing time would be useful to you, you can contact the Disability Support Service Office, DSS, go through their website, call them, send them an email, or talk to me and I can help you get in touch with them. And arrangements can be made based on your situation to help accommodate whatever situation you have. So, some students have test anxiety maybe and benefit from having extended testing time, or have difficulty reading under a time constraint and want extended testing time. If we're in an actual physical classroom, some people have trouble seeing the board or have trouble writing notes while they're trying to concentrate on the lecture, right? So you can have a note taker who will come into class and take notes and give them to you. There's all kinds of possibilities. Okay, our goal in this course is for you to work really hard and sometimes struggle to learn discrete structures. Okay, that's the goal. If that's happening, you're getting your money's worth. I don't want people struggling with things like my mind goes blank when I take a timed test, and so I can't get a good grade on it, and I don't know what to do about that, right? So that's the kind of thing we can talk about accommodations for. All right, college-wide policies. The one I want to read for you verbatim is the non-discrimination policy, because I want everybody to have heard this at least once from one of their teachers. Okay. So non-discrimination policy. Clark College affirms a commitment to freedom from discrimination for all members of the college community. The college expressly prohibits discrimination against any person on the basis of race, color, national origin, disabled veteran status, sex, sexual orientation, age, gender identity, creed, gender expression, Vietnam-era veteran status, religion, marital status, and the presence of physical, sensory, or mental disability. The responsibility for and the protection of this commitment extends to students, faculty, administration, staff, contractors, and those who develop or participate in college programs. It encompasses every aspect of employment and every student and community activity. All right. So think about that if you haven't before, and keep it in mind. Okay. And if you find yourself on the receiving end of something that violates this, come and talk to me. Okay. If you're not sure, if something feels off, but you're not sure if it's actually a problem, come and talk to me. Okay, we can always discuss this and go from there. All right, Code of Student Conduct, you can click through here and see this, but it's all pretty common sense, boilerplate stuff. Engineering, computer science course policies, you can find letter grades and things like that there. That's the basic syllabus, okay, pretty straightforward. Additional course details and policies. So these are the things sort of specific to this course. So this is for fall 2020. So meeting times, instructor, office hours, office, you can see all of that on Canvas. I've set up a Discord server for the course. You can click through to that from the Canvas page. It'll take you to an invite, and you can go ahead and accept that if you like. Discord is not a required piece of this course, and it's not an officially sanctioned part of this course. Okay, it's out there as a resource for students, and if it works for you, that's great. If it doesn't, that's okay too. The one thing I will say is that if this becomes a problem, if people are being harassed on here or something like that, I'll have to shut it down. And that would be unfortunate, because especially for the CS215 class, this seems to be a really good resource. But I'll never require you to use it, okay? I won't post an assignment on here that I don't also post on Canvas, for example. But it's a resource. If you like Discord, you're welcome to join the channel and see what's there. And my suggestion on Discord versus email, you can always email me, right? If I don't want to answer the question, I'll tell you I don't want to answer that. But good questions for me are, I have something coming up on Friday and I'm going to miss class. Is that a problem? Is there something I should read on my own to get ready for that missed lecture, right? That's a great question to ask me in email. Something like, I really feel like I'm struggling with this material. Should it be this hard? That's a great thing to send me an email. But if you have a question like I forgot what we're supposed to do on question 4 that he mentioned in class, right? You can try that on the Discord server, because probably other people remember, right? You can also email me. But it's an opportunity to sort of get more engaged with other people in the class, and the more you do that, the more fun the course will probably be. Or what day is the final exam? Well, if it's the day before the exam, ask me what day the final is. But, did we miss a lot in class today? Or did he say anything about such and such, or stuff like that, right? Discord will work. Interactive Q&A system. So one problem I've been working on with Zoom meetings is they don't feel very interactive. I'm here talking and you're at your computer listening and maybe doing other stuff, but we're all separate, right? There's 30 of us plus me, and we're each in front of our own computer doing our own thing, that's a difficult environment to learn in, right? That's great if you want to take, you know, a YouTube course, but I really want more interaction in the classroom like we have when we're together in the same physical space. So I'm going to be using a Q&A system, and we'll dig through the details of that today, and see how that works. So we'll come back to that in a little bit. Additional policies: exams are closed book, open note. Turn your work in on time, preferably by starting it early. If you started early and you feel like there's going to be a problem with finishing it on time, talk to me early, okay? If you start the homework the night before it's due, you might have, 15 questions about how do I do this, how do I do that. You're probably not going to get 15 answers from me, right, if you write me the night before, because it's logistics, right? So plan on getting your work turned in on time. And if something, that you can see down the road is an issue there, talk to me about it as soon as possible. There'll be a couple of programming assignments in here. We'll talk more about those when we get to them, and also about doing them on the CSE server. We'll talk about that, and we'll go through logging into the server later on today, and programming style. All right. If questions come up, now or during lecture or anything like that, anytime along the way, you're welcome to use your microphone and just say, excuse me, can you repeat that, or I don't understand this, or something like that. You're also welcome to chat. And so some people have done this already, but let's go ahead and just hop over into the chat window, and let's just send a message and make sure that everybody knows how to chat. And you can send it to everyone, or you can send it privately. Doesn't matter. All right, cool. Lots of messages coming in. Good stuff. All right, good deal. All right, awesome. Lecture videos will be posted after the lecture, and you can click through them on Canvas. They're all in one channel now. So here's the 224 lectures from this morning. This first lecture might be interesting for you using the Q&A system. We're going to go through this today, and the rest of these are mostly relevant for the 224 class. But CSE215 will pop up in here every Monday, Wednesday, Friday, and the lectures will be there. I'm not posting the lectures so that you can skip class. Okay, I'm posting them so that you can come to class and concentrate on trying to understand and participate during class instead of trying to furiously write down everything that's being said. Because we're going to go through some of this material pretty fast, right? Well, not fast, but there's going to be a lot of material we're going through. It's going to be very, very dense. And trying to write all of that down while you're listening and while you're understanding can be hard. So everything will be recorded and posted, and that will be available for you. During lecture, you'll see sometimes things pop up here, a little message like timestamping of videos. Okay, when I start a new topic, I'll try to put a little pop-up here that'll tell you, visually we're starting a new topic, like we're talking about timestamping videos. And when you go to look at the video on YouTube, what you'll see is in the description all those timestamps. And then so if you were in 224A and you wanted to know about Canvas access, you can click on that, and this is where we started talking about Canvas. So hopefully that makes the videos usable, and all of those indexes for all the classes are getting stored on a website that you can click through to, and so you can use this as a searchable index and say, oh yeah, Linux access, that was 224A on September 21st, and it's 35 minutes in. So, all right, and Discord server we talked about already. So let's talk about homework. So, you're going to do written homework, approximately one assignment per week. Okay, starting with your first one that's due on Monday, a week from today. And you're going to write it up and you're going to send in a scan of it, right? Or a PDF if you're producing a PDF. And I'm going to be a little picky about how you write up the homework. Okay, so so I've posted a guide for writing up homework. This is something that if you do this, it will help you in this class. It will help you in a lot of your other classes. Your teachers will appreciate it. Okay? It's basically a way to make sure that the person looking at your homework can follow what you've done, can find what you've done, and can see your train of thought. Because in my case, right, you get a lot of partial credit if I know that you were on the right track and maybe you made a math error somewhere or something like that. So most of this is straightforward enough that you can read through it on your own, but let me give you the punchline. There's details here about you know, crossing things out with a single line. I don't care what your paper size is since you're sending in a scan anyway. But you know, put your problems in order. If you're doing questions 2, 5, and 7, do question 2 and then 5 and then 7. Okay. Otherwise, you know, I do grade question 2 and then I get to the next question and it's 7. I don't see a question 5. You lose points for question 5. Maybe later on I find question 5 written sideways on the back of the last page, you know, and then you get credit for it. But do your questions in order. At the top of each page, put down your name, the class, that's CSE215, the homework number, the date, and the page number, like 1 out of 5, 2 out of 5, and so on. And yeah, technically it could be a sticky note as long as I can read it. And yes, you can do it digitally and then turn it in as a rendered PDF. That's absolutely fine. But I would say unless you're really comfortable, you know, producing documents electronically that have, you know, symbols and notation and so on, don't be afraid to just use pencil and paper. Okay, if you write, you know, even slightly legibly, I'll be able to work with that. And spend your time working on the concepts, right, rather than trying to convince Word that this is where you want this figure to appear, right, or you really want this to be bold-faced even though it doesn't want it to be. All right. And basically the main punchline is just work logically, right? Start at the top of the page and just start working down. And put your problem number on the left of the margin. Make it really clear. This is question 3A. That goes on the left of the margin. Then everything else goes to the right of the margin. And just work from top to bottom. Don't make me do, you know, a little rabbit chase where there's an arrow going up here and then you come down and you fill in a little sideways section here, right, and so on and so forth. Lay it out so that it's logical from top to bottom. The top is where you know, state the thing that you're trying to do, and the last thing is the actual solution, which is like circled or underlined or boxed in or somehow, you know, made to stand out. Here's the answer, right? And then everything above that is the work. So think about the flow of your presentation. That's the main thing I'm after. And we'll iterate on this. If I get your first assignment and there's something in there that doesn't match this, right, I'm not going to take off half your points. But I'll send you a note and say, you know, hey, can you do such and such differently, right? And we'll get to the point where after a few assignments, you're turning in this beautiful homework that's like really easy for me to grade and find all the points that you have coming. All right, so that's the guide for writing up homework, and the first homework assignment is some questions out of the textbook. Chapter 1, Section 1.1, numbers 2 and 4, number 4, number 6, number 8, and then 1.3, number 2. So and that's due in a week. And those are all on set theory, which is the topic we're going to talk about. All right, everybody good so far? All right, so let's talk about accessing the Linux server. So your programming assignments are done in C. I suggest doing them on the Linux server that we use for the 224 class. But we're going to use this interactive Q&A system during lecture. And to use that system, you need to log into the Linux machine. So there's a how-to quick start guide here. And this is taken from the quick start for 224. I just got rid of a lot of the sections. So the Linux machine is called linux.engrcs.com. It's not ctech.clark.edu. Okay, we use our own server for this. Your username is your first initial followed by your last name. It's not your CTC username. Okay, your CTech username. It's your first initial followed by your last name. If your name is Tom Smith, your username on the Linux server is T Smith. Okay, not T.Smith, not T Smith 23, it's just T Smith. Okay, and your password is your CTC link ID that usually starts with a 201 or a 101, so 9 digits followed by an underscore. It's not the password that you used on the CTech server. Okay. If you were registered for 215 as of a few days ago, you should have an account on the system. If you registered after that, you probably don't have an account yet, in which case you want to send me an email. So you have a variety of ways to access the server. One way is to use PuTTY. This is how we use, how we connect to the CTech server, usually in CSE121. The other option is to use SSH. So if you're on a Linux machine, or OS X, you have the SSH command. Open a terminal window and SSH will work. If you're on Windows, you can open a DOS shell, okay, command prompt, and SSH should work from there also. Okay, if you're on PuTTY, you probably know how to use PuTTY. You just put in your login information. So let me show you how to use SSH to connect to the Linux server. So SSH tsmith at linux.engrcs.com, and that'll get you in. Okay, I don't have a tsmith account set up, so I can put in my password, but that person doesn't exist, so I'm just spending my time. So let me go ahead and pretend that my username is Goblin King. So actually I should have set this up with someone else. All right, hold on one second. All right, so let me go ahead and log in as myself. So I'm taking the course. Yes, all hail the Goblin King. Thank you. So I'm taking the course. So SSH. My first name is Nick. My last name is Macias at linux.engrcs.com. Okay, it's going to ask me for my password. This is my CTC link ID followed by an underscore. And if I get that password correct, it will tell me your password has expired. You must now change your password and log in again. First thing you want to do is put in the same password you just typed in. Okay? It's asking for the current Unix password. That's the one you just used. If you get that wrong, it kicks you out. Okay, so log in with your CTC link ID followed by an underscore. When it says put in your current Unix password, CTC link followed by an underscore. And then it asks you for a new password. And then it asks you for the new password again, and then it logs you out. Okay, if you go through all that and you see this message that says password updated successfully, you've changed your password. So now I can log in again, and I can use that new password I just set up. And you notice when you're typing, it doesn't show you anything. You don't see stars or anything goofy like that. It just types silently. Right, now I'm logged in, and I'm good to go. All right, so this is a good time for everybody to try to log in to the Unix server right now. And like I say, if you signed up on Canvas more than the past few days ago, or more recently than the past few days, you may not have an account yet. Send me an email. I'll set it up for you after class. But go ahead and try logging in. Let's make sure everybody gets connected. And it looks like about half the class is logged in already. Okay, here's more people coming. All right, cool. And when you're logged in, if you ever want to see who's logged in, there's a command who, which shows you who's logged into the system, right? So you can run that and see people's names. All right, so let's so go ahead and log in if you haven't, but let's go on. So let's talk about the Q&A system. So like I say, I want the class to be more interactive. So I have a system set up where I can post a question to the class and people can respond to it. So we have a couple of options here. We have a chat window, right, which you know, is part of Zoom, and that's always a good way to, you know, send out a quick message, either directly to me or to the whole class. Okay, and I'll usually see those eventually. But we're also going to use this Q&A system. And the way that you do this is, let me go ahead and log back in. The way that you do this, once you've logged in, you just type the word answer. And if I've posted a question, you'll see something like this pop up. And it will show you the question up here and give you an area down here where you can type an answer. And so there's a test question up right now, right? Which just, you know, it's not really a question. It's a welcome message. It tells you we're going to use this to do answers and questions during lecture. And then there's a question to answer, which is, what is your favorite color? And I can say something like red. No blue. And you can click on submit, or you can hit the tab key to come down to submit and then hit an enter key. Either way, and if you type a lot and you want to get rid of it, you can always clear your text by hitting that. And once you submit it, that window disappears and it says waiting for a question from the teacher, and you won't see anything until I post a new question. So so we won't use this today because I've got questions up for other classes, but starting Wednesday we'll use this for some back and forth, playing around with interaction. So if you want to get out of this, hold down Control and press C. So CTRL followed by C while you're holding down Control. That's the standard way to kick out of a program. If you do Control Z, it does something totally different, so don't do that. Just do Control followed by C like cat, and that gets you out of there. All right, I think that's more or less it for logistics and administrative stuff. Any questions on any of that so far? So yes.
I have a question. So when we log into the server, it says like last logged in from an IP address that it lists. Is that our IP address? Because I thought they moved to like IPv6.
That should be your IP address, yeah.
Okay, because it gives you an IPv4 address.
Mm-hmm.
It's kind of
So there's still a lot of IPv4 in the world, um, and depending on where you're logging in from, right? I mean it. So like I have IPv4 address, and I also have a 6. Um, it's kind of in transition, I think. But yeah, that should be the IP address you last logged in from.
Okay.
All right. Any other questions, comments? All right, cool. So let's talk about set theory. Well, let's talk about the course first of all at large. Discrete structures. What does discrete mean to us? What do we think of when we talk about discrete structures? Um, Anybody got any ideas? And you can post in chat or you can use your microphone. But the word discrete, what does that word mean to us? What comes to mind?
Does it mean like distinct units?
Exactly, yeah, distinct units. Somebody said individually separate or distinct. Stuff with space in between them, right? So, you know, if I think of numbers on a number line, 1, 2, 3, right? There's space in between them. I can draw a circle around 1 and 2 and 3, and those circles do not touch each other, right? So those are discrete in some sense. If I take a ruler, right? There's a 1, 2, 3, 4, 5. Those have space in between them. If I go down to millimeters and centimeters, right, 1, 2, 3, 4, 5 centimeters, those have space in between them. If I look at the millimeter marks, here's 60 millimeters from the beginning, here's 61, 62, 63. There's still space in between those. They're still discrete. These quarter and eighth and 16th marks, there's space in between. But can you think of an example of something that's not discrete? Something where we have things that don't have space in between them.
Analog signal?
An analog signal. If you have an amplifier and you're turning up the volume of a signal, your knob might be labeled, 1 through 11. But when you turn the knob a little bit, the volume goes up a little bit. And if that's too loud, you can probably notch it down a little between where it was and where it is now. And if that's too soft, you could probably make it a little louder, right? If you have a really, really fine volume knob. So think about real numbers, because that's really what we're talking about when we think about like an analog signal. Think about your real number line. Well, here's, 1.2, and here's 1.21. Is there a number in between those?
Yes, 1.205.
Yeah. Is there a number between 1.205 and 1.21? Yeah. Any two numbers that I pick on this line, there's always another number in between them. So the set of all the real numbers are in some way so close together to each other that there's no empty space in between any pair of numbers. Okay, that's something that we call continuity. Or we can say the set of real numbers is somehow continuous. So somebody else said a color gradient. That's another example of something that's continuous, right? You could smoothly change a color from one mix of colors or one hue to another. Now your eye may not notice that difference, right? But there's theoretically a continuum of colors available. So real numbers, right? They're an abstract construct. They're something that we dreamed up as humans, and they have this peculiar property that, you know, between any two real numbers, there's always another real number. And that's not true with whole numbers, right? Because I can find 2 and 3, and there's no whole number in between there. So these are discrete, and real numbers are continuous. All right, we're mostly going to talk about discrete things in this course, discrete structures. But even with this property that, you know, this stuff is separated out by spaces, we can do a lot of interesting things in thinking about and analyzing discrete systems. And there's some marvelous properties that you find when you have this discretization as opposed to continuity. There's other properties that you get by being continuous, right? A lot of stuff that we encounter in calculus, for example. But we're going to talk about discrete stuff. And we're going to start off looking at discrete structures by looking at set theory. And sets are a classic example of a discrete structure. So what do we mean by a set? Let me give you a working definition. A set S is an unordered collection of things. So here's a set consisting of a remote control and a pen and a ruler. It's a set containing 3 things. And it's unordered. It's exactly the same set as a set consisting of a ruler, a pen, and a remote control. Okay, the order in which I describe the elements of the set has no effect on the set. It's unordered. What is in the set? A remote control, a ruler, and a pen. Okay, that's the essence of the set, or the things that are in it. And these things that are in it are called members or elements of the set. So that set I just described consisted of 3 things, and the members of the set were a pen, a ruler, and a remote control. And I can say, you know, is a pen a member of the set? Yes, it is. I can say, is a napkin a member of the set? No, it's not. And for anything that I can think of in the entire universe, I can say, is that thing a member of the set? And the answer is yes or no. Okay? Really simple concept, but really rich in complexity in some ways, right? And it's very rigid. You know, something belongs to a set or it doesn't belong to a set. It's a member or it's not a member. But we're going to see some interesting aspects of that. And at the end of the week, we'll talk about something called Russell's paradox. And Russell's paradox comes from this word things. Because our set's allowed to contain rulers? Yeah, we can allow that. Our set's allowed to contain napkins? Yeah, we can allow that too. But we have to be a little careful what kinds of things we allow to be in sets. And if we just take a kind of willy-nilly definition, the set's just a collection of things, we'll find we've introduced some possible paradoxes. Russell's paradox will be one of them. So we'll have some fun on Friday breaking this whole system. But for now, set is just an unordered collection of things, okay, or objects. And they're called members or elements. So we write a lot of symbology and we use a lot of terminology. Discrete structures is inherently, it's largely a math course. And so anytime you get math in the mix, we're going to introduce symbols, and some of it's going to be Greek. So let's do our first Greek symbol here. If X is an element of the set S, we can write the following. X is a member of S. And we write this little epsilon symbol to mean membership. And it's not the epsilon from epsilon delta proofs in calculus. We'll stay away from that. Okay, so X is a member of S. If X is not a member of S, then we can write this thing. X is not a member of S. So that's our first useful notation, symbol for membership. All right. We have different ways of representing sets, of describing sets. So one way is to, just describe all the objects in the set, a ruler, a remote control, and a pen. But that doesn't always work very well. We want richer, more powerful ways to describe what's in a set. So we have some notations. For describing sets. So let me I don't know if I'm going to stick with this time stamping, but we'll see if it works. So set notations, how do we describe things that are in a set? One way to do this would be, for example, S equals the set 1, 2, 3, 4, 5. Right? That's fine if we just want to list the elements 1, 2, 3, 4, 5. But suppose we wanted a set that contained all positive integers. Right? We could say something like, set T equals 1, 2, 3, 4, 5, ... etc., etc., etc. Right? Now this can be a little slippery, right? Most of us, if we saw this, the ... to us would mean 6, 7, 8, 9, 10, right? All the positive integers. But it's not totally without ambiguity. Right? For example, suppose I say P equals 3, 5, 7, ... Well, we might look at that and say, okay, this is all the odd integers bigger than 1. 3, 5, 7, 9, 11, 13, 15, and so on. But I could also mean all the odd prime numbers. If you know what primes are, numbers that aren't divisible by anything except themselves and 1, in which case P would be 3, 5, 7, 11, 13, 17, 19, 23, and so on. So this, if this is ambiguous, don't use it, right? Or put in enough numbers so it's clear. But informally speaking, when we're just, hanging out with our friends talking about sets, we'll use this notation to describe the things that are in a set. But we can get more explicit. We can be more careful about this. So so here's another way to do this. We could say S equals the set of all n such that n is an integer greater than or equal to 1. So we're putting curly brackets down here. Curly brackets mean set notation, right? We list things inside curly brackets. But we're using this funny symbol. We're saying the set of n such that, and the colon means such that, and then we have the rest of this. N is an integer greater than or equal to 1. So we'll use this notation, S equals curly brackets, something colon something else. and it means the set of this stuff such that this other something else. So we could define a set E, the set of all integers, all integers n such that n is divisible by 2. E is a set of all integers n such that n is divisible by 2. Well, that defines the set of even numbers. I could also have said E equals the set of all n such that n is an integer and n is divisible by 2. So there's not usually one correct way to do this, right? There's notational options here. Oh, someone's flashing back to Calculus 3. Yeah, that's good. All right, so this is one way to describe sets. Another way is to use something called interval notation. And this works with numbers mostly. And we have to know what kinds of numbers are we talking about. Are we talking about integers? Are we talking about real numbers? And so on. But here's an example of interval notation. Square bracket a comma b. And this is a shorthand for the set of all x such that x is bigger than or equal to a and x is less than or equal to b. And you've encountered this in other math classes, I believe. But the square bracket is significant. The square bracket corresponds to the less than or equal to. The square closing bracket corresponds to the x less than or equal to b. So for example, if I had a real number line, and I wrote square bracket 2 comma 3, what I mean is all of this stuff in here, including 2 and including 3. If instead I use parentheses, that's the set of all x such that a is less than x and x is less than b. So if I write parentheses 0 comma 1, what I mean is all the stuff between 0, 1, but not actually including 0 or 1. And sometimes we represent that by drawing a little circle at those endpoints to say it does not include 0 or 1. So this might be the parentheses 0, 1, and this would be the bracket 2 comma 3. And we can mix these notations. For example, we could say, bracket 4 comma 6, close parentheses. This is a set of all x such that x is greater than or equal to 4 and x is strictly less than 6. So that's another way to describe sets using this interval notation. So something I like to mention sometimes in this course is that a lot of times we deal with what seem like very simple concepts, sometimes almost ridiculously simple concepts. And this is a pretty simple thing, right? Just everything between 2 and 3 including the ends. Everything between 0 and 1 not including the ends. What's fun about discrete structures is sometimes these really simple seeming concepts actually are gateways to something very deep and complex. And I'll give you an example. This type of set where we're not including the endpoints, this is something called an open interval. In a sense, it's open on the ends. It's got all the stuff in here, but it's missing the endpoints. This setup here where we're including the endpoints, we call this a closed interval. Just more definitions, right? It turns out the study of open and closed intervals is a whole subject in itself. It's something called point set topology. And if you study point set topology and you narrow that subject down to a very particular aspect of it, you end up with something called calculus. Okay? This is the branching point for a very rich, wonderful subject that is a generalization of calculus. Calculus being just one particular version of point set topology. And what's so significant about open and closed intervals? Well, I'll give you one example. Suppose I take this interval 2, 3 inside brackets. All the numbers bigger than or equal to 2 and less than or equal to 3. What is the largest number in that interval? Somebody tell me in chat or on a microphone. What's the largest number in this interval 2, 3? 3. Perfect. All right. Fantastic. How about this open interval from 0 to 1? What's the largest real number in that interval?
It's not defined, is it? Because it's like 0.99999.
Yeah. So, okay, someone got more 9s than you, so that's bigger. But there is no real number that's the biggest number in this interval. And that's a little weird, right? Any number you can think of, I can think of a number that's still in here but is bigger than the one that you wrote down. And yeah, you can do a 0.9 with a line over it, but that's kind of a cheat. Because that's not a number if we have to write out an infinite number of 9s, and in fact you can prove that's equal to 1. But that's usually what we would write down for, you know, a largest number in here. But any number that you claim is the biggest one in here, there's something bigger than that. Just take the average of that and 1, and you get something in here. So just by changing this bracket to a parentheses, we see a very different behavior in here. There's no largest element, there's no smallest element. Whereas here, there's absolutely a largest and a smallest. That's where calculus comes from.
So if you use interval notation, is it not discrete?
We could do interval notation. I was doing real numbers here, but we could do it over integers, right? And then it would be discrete. So over integers, bracket 1, 3 is a set containing 1, 2, and 3. Parentheses 1, 3 would just be the set 2. And in that case, yeah, there is a largest number in here, and there's a smallest number. You can do calculus over integers too, and that gets interesting. But we usually do it over the reals. All right, so that's another way to talk about sets is interval notation. It turns out that, you know, while there's lots of ways to represent sets, there are some sets that we encounter so often that we want to have a special symbol for them. We don't want to have to repeatedly define them. So special sets, the first one is Z, and we write it with a double line on the diagonal. And this is the set of all integers. So 0, 5, negative 17, 1,712, all integers. Okay, it's an infinite set. It also has no biggest number, because any number you can think of, add 1, that's a bigger integer. And it has no smallest number. Yeah, someone said the magic word, aleph. We'll get to aleph probably on Friday or next week. Alright, so Z is a set of all integers. R, with a funny double line, that's the set of reals. We don't do a whole lot with R in this course. Why? Because we're talking about discrete structures, and R is not discrete. But we'll find uses for it once in a while. Q is the set of what we call rational numbers. Rational numbers are just fractions of integers. So 1/2, 1/3, -5/9, those are rational numbers. The number 2 is also a rational number. It's the fraction 2/1. The number 0 is a rational number. It's the fraction 0/1. In fact, any integer is automatically a rational number. It's just that integer divided by 1. It's a fraction, so it's a rational. But it turns out there are some real numbers that are not rational. Anybody know of one? Pi. So pi is definitely not rational. There's no fraction that's equal to pi. It's approximately 22/7. That gets you 3.1428. That's pretty close to pi, but it's not exact. And there's no exact fraction that's equal to pi. Somebody said tau. That's a good example too. It turns out the square root of 2 is not a fraction. We'll prove that later on when we get to number theory and proofs. The Greeks knew a proof of this, that there's no pair of integers whose ratio is equal to the square root of 2. The golden ratio, E, yeah, these are all fantastic answers. So the set of reals is bigger than the set of rationals, and the set of rationals is bigger than the set of integers. And the set of integers is bigger than what we call the natural numbers. Natural numbers are positive integers. And depending on who you're reading, they might include 0. But they definitely don't include negatives. Because let's face it, negative numbers are not natural, right? You can have a cow, you can have 5 cows. Can you actually have negative cows? It's not natural, right? So, but maybe you can have... Go ahead.
Well, theoretically, you can have like 5 cows and like 1 dead cow, which will count as a -1.
I don't think a dead cow is a negative cow, is it? Because if you mix it with a positive cow, do you get like 0 cows? But that's an interesting thought experiment. But this was a problem for people, right? When however long ago we were thinking about abstractions and we started coming up with this idea of, you know, not 2 cows or 2 apples, but this thing. What is that thing? It's a symbol. You can apply it to cows and apples and people and trees and even time, 2 days, you know. But this thing itself, there's something really magical about this. It's a symbol, it's an abstraction. It lets us talk about arithmetic without having to know if we're adding cows or apples or days or people. We can say 2 + 2 is 4. That's a powerful concept, right? It's one thing to say 2 cows + 2 cows is 4 cows, or 2 chickens + 2 chickens is 4 chickens. But when we can get rid of the specifics and just say this, wow, we just leaped forward some huge number of millennia in our development as a people. But being able to do that kind of thing and then getting to this, that was a huge leap. Because this didn't have any obvious analog to the real world. Right? So using this as the idea that you owe me 2 cows, right, as someone just said, that's one way to interpret this. But that did not come automatically, right? Being able to use it as the absence of two cows, whether they're dead or they've gone somewhere, right? That didn't happen automatically. This had to be developed as an abstract concept. So we eventually moved from the natural numbers, right, so-called because they're natural, to include negatives. And then getting in a 0, and 0 is a whole nother can of worms, right? Because 0 is just like, you know, something bizarre. And then being able to get to fractions where you can talk about a half of a chicken, and that's a little weird. A half a chicken plus a third of a chicken gives you 5/6 of a chicken, right? That's kind of strange. But abstractly, we can talk about fractions. And then we can get to reals, right? Is there anything bigger than reals? Are there some numbers that involve the reals, include the reals, but also include other stuff? Something beyond the real numbers?
I think so, but it gets like super theoretical.
Yeah?
It's
Imaginary.
Like, it's kinda like a symbol, it's like double W or something like that.
Yeah, so someone just said imaginary. We call these things complex numbers. Sometimes called imaginary numbers. Right? You can tell a lot by a name. Why are they called imaginary numbers? Because they're not real. Why are they called real numbers? Because they are real. We're in the same situation as the people trying to understand what a negative cow is. Right? This is so new to us that we still call these things imaginary. It's not a real number. It's just this symbol, I, which is the square root of -1. Well, it's a different kind of number, right? But it's in some sense as non-imaginary as, you know, pi or the square root of 2 or 2. So if you take the reals and you throw in these imaginary complex numbers that include the square root of -1, then you get the set of complex numbers, that's the symbol C. That's as far as we have to go. Because in some very well-defined mathematical sense, C is as big as you have to get to cover every possible number. That's another topic. So we have these symbols for sets that we encounter frequently. Alright, the main one we'll deal with is Z, sometimes Q, sometimes R. We don't really talk a lot about complex numbers. But those are some predefined sets. Another type of set is something called a singleton set. And a singleton is just a set containing a single element. So that's a singleton set. That's a singleton set. The set containing a misspelled ruler is a singleton set, right? So a set containing one thing. And those are usually pretty easy to represent just by listing all the members, because there's only one member. Alright. A really special set is called the empty set. And here's an example of an empty set. S equals the set of all x, such that x is bigger than 5 and x is less than 1. So all the numbers that are bigger than 5 and less than 1. Are there any such numbers? Yeah, someone said nada, right? You can't think of a number that's bigger than 5 and less than 1, because if it's bigger than 5, it can't be less than 1 by definition. So if we were to list all the elements in this set, that's what it looks like. It's just nothing. So this is called the empty set. And we have a special symbol for it, which is a 0 with a slash through it. Someone asked square root of 36. I don't know what that question is about. 6. Alright, so the empty set is a special set that contains no elements. And it's actually a really useful set. And we can do some fun playing around with the empty set. So here's another set called T. And it's a singleton set. It contains one element. And what is the element contained in T? It's the empty set. Now T itself is not empty. It has one element. But remember, we started off by saying, right, a set is an unordered collection of things. Well, the empty set is a thing, so I should be able to have a set consisting of that one thing, which is the empty set. That's a perfectly valid set. That's completely well defined. So this is the set containing one thing, where the thing is the empty set. And that's part of a general thing we could do. I could make a set containing 3 things. This might contain the letter X and the number 5 and the set of positive integers. This set contains 3 things: the letter X, the number 5, and a set of positive integers. The fact that this set happens to be really big doesn't change the fact that there's 1, 2, 3 things in this set. So this is where some of the slippery stuff is going to start to come in. Yeah, setception, nice. And we can make all kinds of interesting sets. Here's a set containing 2 things. It contains a set of integers and it contains a set of reals. Does it bother us that the set of integers is actually part of the set of the reals? No. Because this is one thing, this is another thing. Those are different things, so there's 2 things in the set. But those things that are in the set are themselves really huge. Just like if we had a set of an elephant and a galaxy, right? That set contains 2 things, but the elements themselves are really big. Not a problem. All right, let me leave you with one more definition: equality of sets. So A equals sign B means set A and set B are equal. And what does it mean to say 2 sets are equal? Informally, we can say they contain exactly the same elements. So 2 sets are equal if and only if they contain exactly the same elements. For example, A could be the set 1, 3, 5. B could be the set 3, 5, 1. A is equal to B. Why? Because they contain exactly the same elements. Remember, the set is unordered. This contains the elements 1, 3, and 5. This contains the elements 1, 3, and 5. Those are the same set. If C equals 1, 3, 5, and 6, then A and C are not the same set, because this contains 135, but this contains 1356. So we write A is not equal to C. So somebody asked if we write that and we write this, are those the same set? Well, it depends what you mean by this, and I would say that when you write this, you haven't given me enough information to know what this set is. This is really kind of a bit of an informal shorthand. If you write this and you hand it to a reasonable person, they'll probably assume this is all the integers bigger than or equal to 0. But this with just a 0 dot dot dot, it's hard to know. So I'd say I don't know the answer because that's a notational question. But if you use this dot dot dot, it should be unambiguous what you mean. And it kind of depends on the context. If we're talking about, you know, sets of consecutive integers, then it's probably going to be pretty clear what we mean there. All right, let me give you a formal version of this. So A equals B means the following. For any x, x is a member of A if and only if x is also a member of B. So for anything that you can think of in the entire universe, the number 1, the number 3, a flying cow, that element belongs to A if and only if it belongs to B. If that is true for any x, right, then and only then can you say A is equal to B. So my set's over here. A is 135, B is 351. If x is equal to 1, yeah, it belongs to A and it belongs to B. If x is equal to 17, it does not belong to A, it does not belong to B. Right? It belongs in here if and only if it belongs in there. With A and C, if I pick the number 6, A does not belong to A, but it does belong to C. Well, this says x must belong to A if it belongs to the other sets. So since 6 is a member of C, it would have to be a member of A for A and C to be equal. Since it's not, that's enough to say right there A is not equal to C. So we understand this intuitively, but it's important to have definitions because our intuition will start to fail at some points. And so when we say two sets are equal, it means for anything in the universe, it belongs to this set if and only if it belongs to that set. Belongs means member of. Okay, so somebody posted an interesting question. What about these two sets? So I'm going to say right now, let's not ever list a set with an element listed more than once. It's a sort of notational typo, right? When we list the elements of a set, we're listing you know, all the things that belong to it. So if you're going to the store and you want to make your grocery list and you want to get apples, you don't say apples, 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 right? You only have to list it once. It's on the list. It's in the set of things that you're going to pick up from the store. So if I was forced to say, you know, is this the same set as that? I'd say probably yeah, but I would actually say, you know, that's not a well-defined set. That's not a proper use of the notation. So somebody else said square root of 9 and 3 negative 3. Well, again, it kind of depends what we mean by square root of 9. Usually in a math class, when we say square root of 9, we more often than not mean the positive square root. But technically, right, the square root of 9 is not a well-defined function. It has two values, positive 3 and negative 3. And if that's what we meant by this, then yes, those two sets would be equal. But let me show you a different way to write this, the set of all x such that x squared is equal to 9. Well, that's exactly the same as this set. And this is really how the square root can be defined. What's the square root of 9? It's the set of all numbers whose square is equal to 9. So that would be a more formal way to write this. And in that case, x could be 3 or it could be negative 3. And a lot of this business of sets of numbers comes from working with equations, right? So if you start with whole numbers, this is where it's a subject tag. If you start with whole numbers, right, we can say something like, you know, x plus 1 equals 5. Right? And the solution to that is x equals 4. Well, that's not a problem. But if I want something like x plus 5 equals 1, I'm forced to move to negative numbers, right? The only solution for this is negative 4. I mean, this is a pretty simple equation, but by just changing around the numbers a little, I can't solve it if my whole universe consists only of positive integers. So suddenly I need a negative integer. And now if I write something like 2x equals 6, I can solve that. And 2x equals negative 6, I can solve that. But 2x equals 7, I can't solve that with integers. Suddenly I need to come up with fractions. And I might have fractions in my universe now. So I've got positives, negatives, I've got rationals. But here's another equation that I cannot solve with fractions. I've got to introduce an irrational number. And here's an equation that even if I have irrational numbers, I still can't solve this. I have to bring in imaginary numbers. So this development from, you know, whole numbers to whole numbers including 0 to negatives to fractions to complex numbers, you can sort of trace that development through, you know, what happens as you extend your set of equations that you're trying to solve in life. That's something to think about. All right, so I think this class technically goes until 2:05, but Mondays I have another class that starts at 2. So I'll double check what the official ending time is, but Mondays will generally end about 1:55. So I'll call it good for now. Make sure you know how to log into the Linux server, because we'll start using that on Wednesday. If you can't get logged in, send me an email, nmaciasclark.edu, and we'll figure out how to make that happen. Otherwise, go ahead and you can start looking at the homework if you want, but we'll get through most of what you need to do the homework in Wednesday's class, and then we'll go from there. All right, thanks everyone. Have a great day. I will see you next time.